This video is about the effects of thermal energy. The learning objectives are to infer that solids, liquids, and gases expand when heated and contract when cooled. Also, we will describe the effects and applications of expansion and contraction in everyday life, and discuss the strange expansion of water. Thermal expansion at the molecular level shows that when a material is heated, the molecules vibrate more and their average distance increases. This increased spacing results in the material expanding in length. A solid expands when heated and contracts when its temperature decreases. In the ball and ring experiment, before heating, the ball fits through the ring. We will continue this experiment on the next slide. The bar and gauge experiment demonstrates that the bar fits into the gauge when cold. If you heat the bar, will it still fit? What happens when it cools down? The bar breaker experiment shows that the steel bar is heated and tightened. When the bar cools down and contracts, what happens to the cast iron rod? What conclusions can be made about the force of contraction? Different materials expand by different amounts when heated through the same temperature increase. As shown in the table, materials like aluminum expand significantly more than others, such as Invar. Observing the expansion of liquids, Fig. A shows a glass flask with colored water. Initially, in Fig. B, the water level falls when heated. Later, in Fig. C, the water level rises quickly. These phenomena happen due to the glass flask expanding first, then the liquid. The bar breaker experiment shows that expansion and contraction produce a very large force, strong enough to break the cast iron rod when the steel bar contracts. To compensate for thermal expansion, railway tracks are laid in sections with gaps. They are held together by fish plates and fastened by bolts through oval holes. These gaps and oval holes allow the tracks to expand without buckling. Bridges use rollers and gaps at one end to compensate for thermal expansion and contraction. This prevents the bridge structure from being damaged by seasonal temperature changes. Pipelines carrying hot gases, such as steam, require expansion joints, often in a ring form. This joint allows for the expansion of the pipe, preventing structural damage. Overhead power lines and telephone wires expand in summer and contract in winter. They are installed with slack to overcome this problem, preventing them from snapping in cold weather or sagging too much in hot weather. Concrete pavements are laid in blocks with gaps or joints. These joints allow the concrete to expand or contract during hot or cold weather, preventing cracking and damage to the surface. A bimetallic strip consists of two different metals, such as brass and iron. Brass expands and contracts more than iron. This difference in thermal expansion causes the strip to bend when heated or cooled. One application of a bimetallic strip is in a fire alarm. If heat from a fire causes the strip to bend upwards, it completes the circuit, and the alarm bell rings. The bimetallic strip is also used in an electric iron as a thermostat. As temperature increases, the strip bends and breaks contact C. When it cools and straightens, contact C is made again, regulating the temperature. Hot riveting is another application. A hot rivet expands, and when hammered, it forms a new head. As the rivet cools and contracts, it tightly pulls the two metal plates together. This graph shows the volume of water against temperature. Note how the volume is smallest at 4 degrees Celsius, confirming water's unusual behavior. The graph of density against temperature of water shows that water is densest at 4 degrees Celsius, reinforcing its unique expansion and contraction characteristics. Due to this unusual behavior, water at the surface of a pond sinks during winter when it reaches 4 degrees Celsius. Even if the surface freezes, the fish beneath can survive.